Welcome to Final Research Group YouTube channel. Don't forget to subscribe and share.
Subtopic that has to do with Hilbert spaces. Hilbert spaces today. Um, okay. Before we go to Hilbert spaces, we define what we call inner product spaces. Of course, we define all of this in in a linear space. In a linear space. So if you have X, which is a linear space, X is a vector space, and then this vector space is endowed with some inner product. Inner product is actually a function defined on X, and you have, map to C. Generally, that's from, it can be S to X, X could be R, it could be C, just fields, and these are linear spaces. So of course, R and C is the commonest ones. So it could be R or C or even any other structure that is a vector space. So that will satisfy certain axiom is a function that will satisfy certain axiom. And those axioms are as follows. Number one, maybe I call it I1. I1 is that the inner product of X, X is always positive, greater than or equal to 0. And also, inner product of X, X is equal to 0 if and only if we are dealing with a 0 vector. If and only if X is a 0 vector. Okay? So that was the first axiom. Well, let me share another screen. So I'll be able to do more justice to that. Remember, we are trying to define inner product. Because of the fact that I want us to remember all the properties, I better have to remember the first one. The first one, we said that inner product of X, X is greater than or equal to 0. And not only that, inner product of X, X is equal to 0 if and only if you are dealing with a 0 vector. Okay, that's the first axiom, I1. The second axiom, I2, is that inner product of X, Y is the same thing as inner product of Y, X. This is a symmetry, but then because you can be dealing with complex numbers, you talk about inner product of X, Y being equal to the inner product of Y, X conjugate. This bar on top is conjugate. I'm sure you know what we call the conjugate of complex numbers. For example, if you have a complex number Z1 to be equal to 2 minus 3i, Z1 conjugate is what? 2 plus 3i. I'm sure you know that. Huh? If you have Z2, a complex number to be 5i, okay, Z2 conjugate is what?
Negative side.
Minus 5i. I'm sure you. So yeah, you know all that. So if you are, because this x and y could be complex vectors. So I comma inner product of x comma y is equal to inner product of y comma x conjugate. That's I2. I3 is that inner product of lambda x, inner product of lambda x plus mu y comma z is equal to inner lambda. This lambda now comes out lambda inner product of x comma z plus mu. Remember that this multiplies the that's, but then the lambda is out. I can go out. It's a constant, not affected by the inner product. And the second constant is mu yz. So you have mu inner product of y comma z. Okay. Meanwhile, x, this will, all of this I1, I2, and I3 will happen for all x, y, z in x. I'm sure you remember x. Our x is our linear space. Y, lambda, and mu, the constants, lambda and mu, lambda and mu, they are from C, you know, they are constant, complex constants. Okay, so that's the definition of an inner product. Inner product being a function. A function, first of all, you define the function inner product of from E or from x cross x to C, okay, which could be K. If you like, let me not say C, but K. K is a linear space, which is either R or C in a general term. So that's K. That's S cross S2. It's a function that satisfies the following item, three items. The first item is that inner product of S comma S is always greater than or equal to 0. And then inner product of S comma S is 0 if and only if X is a zero vector. The second axiom is that inner product of X comma Y is equal to inner product of Y comma X conjugate, right? And then the last one, number 3, is that inner product of lambda x plus mu y comma z is equal to lambda inner product of x comma z plus mu inner product of y comma z. All of these x, y, z are vectors in x, in the linear space. Y mu and y lambda and mu are complex constants generally. So, or if all these axiom I1, I2, I3 is satisfied, if I1
sorry, sir.
to I3, yes.
If K is R, lambda mu not in R?
Yeah,
Or they
if
are
K
always in C?
is R, lambda mu is in R, of course, will be
Okay,
in
sir.
R.
Okay.
Okay. In
Yes,
fact,
sir.
if we are even dealing with R, if our space is in R, this and this, there will not the bar in R is not necessary. I mean, does
Yes,
not
sir.
change anything.
Yeah.
In fact, we are still coming to all those remarks. We'll make such remarks later. If we are dealing with R, some of like this one, symmetry will hold without necessarily bar because the conjugate. Because when you do the conjugate of a real number, it doesn't change anything. For instance, what's the conjugate on 4? 4 conjugate is still 4, right? Is it not? And 3 conjugate is 3. Okay, such that if these are real numbers, the conjugate does not change anything. So, of course, we can pick, we said generally this inner product is a function from, a function from x cross x to k. K is a field, a scalar field, which could be, most of the time, could be either C or R, right? We are going to give examples. Some of our example will be on C, some of our example will be on R, because both of them are fields. Okay, they are fields, so you can pick scalars from them. Okay, so that's the K could be either C or R most of the time. Okay, so we'll pick some example from C, some example from R subsequently. Okay, so let's go to the next slide. Ruben, I think you should send a message across to your colleague so that they also join if you have your platform there.
Okay, so I'll send again.
Yeah. So I give some example. I give some example. Example. The linear space Rn with the function inner product defined for arbitrary vectors in arbitrary vector x. Rn, arbitrary vectors are n-dimensional. So if you pick x, a vector, it will have n dimensions, x1, x2, up to xn. Okay, obviously. If you also pick y, it's also going to be n-dimensional. In other words, you have y1, y2, y3, up to yn. These are objects in Rn. So if you now define your vector by the following, if you now do inner product of x comma y, we define it as follows. Inner product of x comma y, if you define it as summation, I running from 1 to n of xi, yi. We claim that the inner product so defined, inner product as defined above, is an inner product, okay, on Rn. Of course, our linear space is Rn. Okay, well, if it's going to be inner product, the way you define it, if this is going to be inner product, it must satisfy I1 to I3. Is it not? You must show that I1 to I3
Yes,
are
sir.
satisfied to say that this function so defined is an inner product. Okay, so let's share a new screen. I'm sure if you have copied this somewhere, you remember. So we are trying to show that this inner product is an inner product. It means that we have to show that I1, I2, I3 are all satisfied. I'm sure you remember what I1 is said, and what I2 said, and what I3 said. All those axioms of inner product. Okay, so let's go back to demonstrate the axioms. Okay, so for I1, what are we to show? What did I1 say? You recall inner
Inner
product
product of
of what?
x. Inner product of
X
x times
comma
x is
x
greater than 0.
equal to 0. And also inner product of x comma x equal to 0 if and only if we are dealing with a 0 vector. Is it not? So we are going to show this. But remember how in that example, how our inner product is defined. Inner
Equal to
product
0.
of x comma x is what?
The
Summation.
sum of
Tell us.
xi squared from 1 to n. Xi,
Yeah,
xi.
1 to n.
Go xi squared.
Yeah, which will be xi, right? Which will be summation I running from 1 to n of xi squared, right? Like you said. Is it not? Is it not? Obviously, these are vectors square. This will be greater than or equal to 0. Is it not?
Yes, sir.
Is it not? For all I
Yes, sir.
counting
Yes,
from
sir.
1 to n. So if xi squared is greater than or equal to 0 for all I, it follows then that summation I running from, because if all these xi squared is greater than or equal to 0, if you now sum them up, if you sum up things that are greater than 0,
It's
it must also be
greater
greater than
0.
0. Is it not?
Yes, sir.
Now, that's the first part. The second part that is saying x, inner product of x, comma, x, which we have already discussed to be xi squared. If you claim that this is equal to 0, what does that mean? Well, this will happen, this will be equal to 0 if
every
and
xi
only
is
if
equal 0.
xi good equal to 0 for all I, right? For all I, 1, 2, there are n of them, right? This can only be because if one of them fails to be 0, then this sum cannot be 0. Is it not?
It is,
So,
sir.
but then for this to be 0, it means that all the i's must be 0. And if that is the case, this implies that x is a 0 vector, right? Don't forget that x is
Yes,
in
sir.
Rn, which is x1, x2, x3, xn, up to xn. Right? All
Yes,
of
sir.
them is what? 0. Is it not? In other words, x, that your x will look like 0, 0, up to 0, up to n tuples. Right? N tuple of 0. Is it not? So that's how that your
Yes.
x looks like. That will equal to this. Okay? So that's for that example. We are going to look for more examples. I share another slide so we can proceed. Okay, fine. I have yet another example. Example. The linear space Cn. The other one we consider was Rn, but this one is Cn. With the function inner product defined for arbitrary vectors, u, for instance, you have, if you pick u from Cn, it will be n-dimensional vector. So it's going to be z1, z2, z3, up to where? Zn. Is it not? If you also pick another vector w, it's going to be what? w1, w2, w3, up to wn, right? These are
Yes.
vectors U and W. These vectors are in Cn.
Cn.
Is it not? So if you now define the inner products of U, W by summation I running from 1 to n of Zi Wi these Wi conjugates, right? So you can see Zi Wi conjugate, right?
Yes, sir.
So we claim that this inner product is inner product. It's inner product. Okay, so this function is inner product as defined. Inner product of U, W is equal to summation of Ci Wi conjugate. Okay. Well, we can go ahead to demonstrate how that is the case. Okay. So let me share another slide. Remember how our inner product is defined. Okay.
Okay, sir.
Yeah. Okay, so I want to now show it. But before then, recall how the U inner product of U, W is defined as summation I running from 1 to n of Zi Wi bar conjugate.
Yeah,
To
conjugate.
show I1, yeah, to show I1 suffices to show that inner product of U, U, is equal to 0 or greater than or equal to 0, right? For all U. And then not only that, inner product of U, U is what? Is always positive. Yeah, sorry, is equal to 0.
So if
If
we
and
say,
only if, yeah. So by the way this inner product is defined, inner product of U, U will be equal to what? Will be equal to what? Summation I running from 1 to n, right? U Zi
conjugate.
conjugate, right?
Yes, sir.
So this is equal to what? When you do in
Summation
any
of
two complex number, if it will be, this
get the
will be
modulo squared.
summation I running from 1.
And to
Is
modulo
that?
squared.
Yeah. Is it not?
Yes, sir.
Is it not? So which is greater than or equal to 0. This is greater than or equal to 0. I hope you are with me.
Yes, sir.
Are you with me? Okay, thank you. So that's
Yes, sir.
greater
Yes,
than
sir.
or equal to 0. Thank you. So that's greater than or equal to 0. And as a matter of fact, summation I equal to 1 to n of Zi squared will be 0 if and only if Z1 equal to Z2 equal to a whole lot of things equal to Z, and all of them will be equal to 0.
Zero.
Right? In that case, this implies that U is a 0 vector, which can be likened as 0, 0, 0 up to n tuple, and this is an object in Cn. Okay, so that justifies the first axiom. Okay. Let's go for the second axiom now. The second axiom, can you remember the second axiom? Second axiom is saying that inner product of, that's I2. Inner product of U, comma, W is equal to inner product of W, comma, U conjugate.
Conjugate.
Is it not?
Yes, sir. Yes, sir.
Now, let's begin from here. Inner product of U, comma, W, what's that? By definition, is equal to what? Summation I running from 1 to N of ZI WI conjugate. Okay?
Yes, sir.
So, yeah. So, if you do this, if you take the conjugate of this will be equal to summation I running from 1 to N of ZI WI conjugate. You take the conjugate of this, what will it be? This is summation I running from 1 to N of ZI conjugate WI.
Yes, sir.
Okay? So which is equal to inner product of what? W comma U conjugate. Okay, the third one for I3, we argue as follows. We have the following for inner product of
lambda U plus mu V,
yeah,
omega
lambda U plus what?
mu V,
Mu
omega.
mu W, comma, maybe
V.
if you like, let's use another alphabet. Whatever
Yes,
alphabet you use. Okay, so what would this be? This will be equal to summation I running from 1 to where? To
N.
N of
Lambda mu
okay,
plus
let
mu.
me, yes, since that our mu, I want to take some notation that will not be so confused. Let me do this one Y and do this one W. I'm coming, this one W. Since we are using W bar, what I'm trying to say is that I want to use the following. U plus, sorry, let me rewrite this. What I want to do is lambda U plus mu Y, comma, W, right?
Okay.
By definition, I want us to use, by definition, that would be equal to what? This will be equal to lambda u plus mu y. Of course, I will be here. I will be here. This one will be z, if you like. If you like z, right? Zi plus
sir.
mu I. All of these
Omega I
times
conjugate.
wi conjugate, right?
Yes, sir.
So if you express this further, what do you have? This will be, you can open this bracket now, right? This will be summation I running from 1 to n of lambda zi zi wi conjugate plus summation I running from 1 to n of mu yi wi conjugate. I don't know if you understand what I mean. I just opened the bracket. This
Yes,
one
sir.
will multiply this, and then this one will also multiply this, you have that. Is it not? This is equal to, this is a lambda independent of I. This is a constant, is not affected by the counting I, 1, 2, and so I can factor it out. This is lambda summation I running from 1 to n of zi wi conjugate plus mu is also not affected by I, it's a scalar, so I can factor it out. Mu summation I running from 1 to n of yi wi conjugate, right? What's this candidate and what's this candidate? This is lambda inner product of what?
UW.
U W, right? Plus mu inner product of what? Y,
YW.
comma, is it not? So this one is exactly what I3 is saying. If you check, this is exactly what I3 is saying. Okay? Okay, so that's another
Okay, sir.
example. I'm going to give you the next one, then you can check that one as well on your own. Okay. Okay. Yeah. So I give you the next example, which I will now call assignment in a way. Here, you're looking at the linear space. L2. This is the sequence space, but is built on linear space C with the function inner product, okay, defined as follows. Defined as follows. If you pick, of course, in sequence spaces, if you pick x and y, inner product of x and y, you define it as summation I running from 1 to, because in L2 is infinite dimensional. Okay, I'm sure you remember what L2 stands for. So it's going to count from 1 to infinity of xi, yi's conjugate. Okay, this will come from x and y in L2 on C. L2 build on C. Okay. And I'm sure you remember what that L2 is. So the sequence space. So this space is an inner product. an inner product. So you can verify that at home. Okay. It's not far away from what you have been doing. The only thing is that this one runs to infinity. The other one runs to n. But the argument is basically the same. Of course, because L2, it runs to infinity because L2 is infinite dimension. I'm sure you remember L2, how it looks like. L2C. You are looking at X. If you claim that X is in L2, you are saying that this X can be written as X1, X2. It can never stop, such that summation I running from 1 to infinity of xi squared is less than infinity. That's the meaning. So this x1, x2, x3 up to continue. The summation I from 1 to infinity of the modulus of xi squared, the sum of all of them must be convergent. That's the meaning of an object or a vector belonging to L2. So, and the inner product is defined as follows: summation I from 1 to infinity of xi dot xi dot yi conjugate. Okay, so you can show that is a linear space. Okay, maybe we need to even demonstrate more examples, and before we go to the basic properties, other basic properties of inner product space. Okay, I give you more examples. If I have the following example, the linear space, this time around, let's deal with function spaces. So the linear space, C, that's the space of continuous function defined on closed and bounded interval 0, 1, with the function inner product, okay, defined for arbitrary functions fg, of course, functions fg in this space, in the space of continuous function between 0 and 1, close bounded. And that inner product is defined as follows: the inner product of f, comma g is defined as the integral from 0 to 1 of f of t dt. Of course, you are integrating with respect to t. So we are claiming that this inner product is an inner product. Okay? It's an inner product.
Is it
Of
JT
course,
or DT?
for you to do that, this is dt. ft gt, ft gt dt. Okay? I don't know if you understand. This gt.
Okay, sir. Okay.
Ft gt dt. Okay? So let's maybe we verify that one before we now proceed further. Well, if you look at the way the inner product is defined, inner product of fg is defined as integral 0 to 1 of ft gt integrating with respect to t. I1, you need to show that inner product of f, f is greater than or equal to 0, right? Inner product of f,
Yes,
f as defined is integral 0 to 1 of ft dt, right? Which is integral 0 to 1 of f squared t dt, right? So this function as defined, this function as defined is a continuous function, and you discover that this function as defined is, if you integrate this will be this function, obviously the square of it, since a continuous function from 0 to 1 will always be greater than or equal to 0. Okay, if you evaluate between 0 and 1, okay,
Yes,
it will always be greater than or equal to 0, provided you are not dealing with a 0 function. Okay, so that's that. And then integral of the integral of f comma f, which is in 0 comma 1 f squared t dt, is equal to 0 if and only if, you know, f is equal to 0. That is, if you do integral 0 to 1 of 0 squared with respect to t dt will be 0. So this will be 0 if and only if this satisfying I1. Okay? Satisfying I1. For I2, you have that inner product of f comma g, inner product of f comma g is equal to integral 0 to 1 f of t g of t with respect to t. Okay, this is descending at 0 comma 1 0 comma 1 g of t d of t conjugate. Okay,
f of t, sir.
conjugate. Yeah, yes, f of t g of t. Why? Because f and g is from C01. They are real values. Okay, they are real values, so they are real valued functions. So the conjugate does not affect anything. I don't know if you understand what I'm saying. So f and g are from C0, 1. That's continuous function defined on 0 and 1. So they are real numbers, really, real valued functions. So the conjugate does not affect anything, unlike if it is complex valued. I don't know if you understand what I mean. So that
Yes.
means that you have shown that f comma g inner product is equal to inner product of g comma f conjugate. So that's for I2. Now for the last one, I3. For I3, you have to pick 3 functions, f, g, and h from C0, 1. Okay, you now do inner product of lambda x, lambda f rather, lambda f plus mu g comma h. Okay, this obviously by definition of that inner product will be what? Will be integral 0 to 1 of lambda f plus mu g h of t dt. Is it not? That's
Yes,
the
sir.
way it's defined. This is equal to integral 0 to 1. You can open the bracket of lambda f of t h of t dt plus integral 0 to 1 of mu g of t h of t, right? This lambda can go out so that the whole of this will translate to lambda integral 0 to 1 of f of t h of t. While the whole of this one will translate to mu can go out. So mu integral 0 to 1 g of t h of t, g of t h of t, right? So what is this candidate? What is that candidate? This candidate, this will be equal to lambda inner product of what? F comma h plus mu inner product of g comma h. This one is g comma h. Is it not? That this one is equal to this. I don't know if you observe what we have shown. Do you understand?
Yes, sir.
Okay. Okay, so we will now go straight to show some properties. Okay. Okay, fine. We will now look at some basic properties of inner products. Basic properties. From I3, we want to look at this property that if you have z comma lambda x plus mu y, this will be lambda conjugate inner product of z comma x plus mu conjugate inner product of z comma y. Okay? Remember I3 gave us I3. By I3 you had, what do you have in I3? I3 you had this one first and this one last. But this property, if you reverse it, what do you have? What I'm saying that you have in I3 is lambda x plus mu y comma z. I'm sure you remember that's what you have in I3. But this property here, you are reversing. Instead of z being the second, z is now the first. And instead of this one being the first, is now the second. That's what's there. So if you have problem like this, you want to show that this is equal to lambda. Lambda is on the other side. But when it comes out, remember when it came out here to the other side, it was not carrying conjugate because that's one of the properties. So it's on the other second coordinate. So it comes out here, it's carrying a lambda conjugate. Mu is also on the second dimension. So when it comes out, it will carry conjugate. Meanwhile, all of this is because of what we already know. So to prove this is very simple. Recall that inner product of z comma lambda x plus mu y, if you want to change the coordinate, remember what we said. We can do so. In other words, I have lambda x plus mu y and then z comma z. We can do so provided that we do conjugate. You remember, this one is by I2. I2 says if you are interested in symmetry, z comma lambda x plus mu is equal to lambda x plus mu y comma z. If you are interested in symmetry, you do the conjugate. Is it not?
Yes, sir.
So the whole of this is equal to, of course, you can, you recall, you can bring this one out. Conjugate is affecting everything. So I can bring it out. Lambda conjugate is still outside. It's a complex number. So inner product of x comma z conjugate, okay, plus mu, this conjugate is already affecting everything, y comma z. So this is by I3. This is by I3. Okay. So, of course, this whole of conjugates, you can break them up so that you have lambda conjugates, inner product of, if I want to reverse this, but then let me break it up first. So I have x comma z, s comma z conjugate plus mu conjugate, inner product of y comma z conjugate. This is exactly property of complex number by property of complex number by property of C. So we use the property of complex number to do this. Now, remember, if I don't want s comma z conjugate, I can turn it around. This will be equal to lambda conjugate. Instead of saying x comma z conjugate, I can say z comma x. Do you remember by I2? Do you
Yes,
remember?
sir. Yes, sir.
Plus this one. This one is mu conjugate. Instead of saying y comma z conjugate, I simply say inner product of z comma y. Right? So that's how we arrived at this. That's how we arrived at this is equal to lambda conjugate inner product of z comma x plus mu conjugate inner product of z comma y. That's how we arrived at that. Okay, so that was one of the properties that we can easily show. Okay. There are other properties, and want to look at them, like the Cauchy-Schwarz inequality and so on. Okay. The Cauchy-Schwarz inequality. Okay. If you let E, for instance, be an inner product, space for arbitrarily we pick up two vectors from E, okay? If you define the modulus of inner product of x comma y all squared, that is less than or equal to inner product of x comma x dot inner product of y comma y. Okay, so this is known as the Cauchy-Schwarz inequality. And as a matter of fact, equality, this instead of this inequality, this equality will hold. Equality holds if and only if x and y are linearly dependent. I'm sure you remember when we said that two vectors are linearly dependent. Do you remember?
When one is
Do you remember?
when y is kx, k in R.
You said when
When y, maybe y is equals kx.
a constant, okay, multiple of that, okay, it's okay. Or if the angle between them is 90 degrees, right? If you are interested in the angle. Okay, that's okay. Let's look at some other properties also in form of lemma. I put this property in form of a lemma. The function norm defined as norm from E to R defined by norm of x equal to the square root of inner product of x comma x. This function is a norm on the vector space E. Okay. Well, you can easily show this. If it's a norm, it must satisfy three functions, three axioms rather. Do you remember? Do you remember the axioms that it must satisfy? It suffices to show
Is greater than 0.
that if it's a norm, it then means that norm 1, norm of x is always greater than or equal to 0, Abi? And also norm of x is equal
0
to
if
0
x is
if
0.
and only if we are dealing with a 0 vector. The second property
Norm
or
of
axiom is
kx
that norm of lambda
lambda x
is
absolute
equal
value
to
of lambda norm
absolute
of x.
value of norm of x. Okay. And lastly, N3, the triangle inequality,
Yes,
right?
sir.
Norm of
Norm of
x
x
plus
plus
y
less
is less
than
than or
norm of
equal
x
to
plus
norm of x
y.
plus norm of y. So these are the three N1, N2, three assumptions that we must show. Okay, but let's try to see if we can show them. Let's try and see if I go to another slide. Remember the norm, remember the function. The function is norm of x is equal to inner product of x comma x, all of them inside the square root. So that's exactly what we want to show, that it is a norm. So I share a new slide and then we proceed. For N1, norm of x, the way it's defined is inner product of x comma x. By what we know about inner product, this inside object is greater than or equal to 0. Is it not? Since this is an inner product, it's already greater than or equal to 0. Do you understand?
Yes, sir.
And the square root of something that is greater than or equal to 0 is also greater than or equal to 0. When an object is positive, the square root is also positive, is it not? Hence, making this one to be greater than or equal to 0. And if you claim that norm of x, which is inner product of x comma x square root, if you claim that this is equal to 0, this will be 0 if and only if inner product of x comma x is equal to 0, if and only if S is a 0 vector. Okay, and this will happen for all x in the domain of your function, which is E. Okay, so that satisfies axiom number 1. So it's okay. So the inner product of S comma S is 0 if and only if S is a 0 vector. That's for N1. Let's go for N2. We go for N2. For N2, you have that inner product of lambda S, by the way it's defined, is equal to the root of inner product of lambda x comma lambda x. Okay, so this of course is equal to you know, this lambda if it comes out, this will be lambda for this one.
Lambda conjugate.
This one, lambda conjugate, right? Inner product of x comma x. I'm sure you remember.
Yes, sir.
This will be inner product of lambda conjugate is simply lambda squared. Is it not? Inner product of x comma x. This will be, you know, the square root of lambda squared square root of inner product of x comma x. This will be simply, if you take the square root of this, it will be simply the modulus of lambda square root of inner product of x comma x. What is this now? This exactly that is what you have shown is that norm of you know, this will be modulus of lambda norm of x. This is norm of x. So you started with this and you show that it's equal to lambda modulus of lambda norm of x. This satisfies N2. I don't know if you understand. Do you understand?
Sir.
Okay, let's show the last one is triangle inequality. So let's try to show that. Well, for triangle inequality, I do the following. Norm of x plus y all squared is simply doing inner product of x plus y, comma x plus y. I'm sorry, I hope you know this is x plus y. You know that I squared both, this is supposed to be square root, but I squared both sides. If I square this side, that square root disappeared. I square this side, that's square.
Yes,
I
sir.
hope you know that. So this is equal to, if you expand this will be x comma the whole of this plus y comma the whole of this. In other words, this will be inner product of x comma x plus y plus inner product of y comma the whole of this y comma x plus y. Okay, you can further expand. This will be inner product of x comma x comma x plus inner product of x comma y x comma y plus inner product of y comma x plus inner product of y comma y comma y. Okay. Well, this is equal to, for this one, this one and this one will be norm of x squared, okay, plus this one will be norm of y squared. If you check this and this will be inner product of plus this plus, okay, plus inner product of x comma y plus inner product of for this one y comma x, I write x plus, I want to write it as x comma y. This is already x comma y. So, but to write y comma x as x comma y, it must be x comma y conjugate. I'm sure you know. Then plus this one is already x comma y. Do you understand what I did?
Yes, sir.
This one is this. This one is this. Now, for this one, y comma x, I want to write it as x comma y. Yes, I can do that, but I have to put conjugates. Is it not? Then x comma y is already there. Do you understand? So, so that this and this will look alike. So if you are now adding, you have inner product of norm of x squared plus plus what? 2 real inner products, because they are now inner product. This x comma y conjugate plus x comma y will be a real number. That's what I'm trying to say. So it will be 2 real inner product of x comma y. There are 2 of them. This plus this twice, but then it's going to be a real number because if you take conjugate of a number plus itself, it's going to be purely real. Then plus the norm of y squared. Okay. Now by Cauchy-Schwarz inequality, this is less than or equal to, I want to share a new slide. You just apply Cauchy-Schwarz inequality on this one. This one and this one is already in the right format. If we apply Cauchy-Schwarz inequality on this, our job will be done. But let me share a new slide so we can do that. Just remember this. This is what we want to apply Cauchy-Schwarz inequality. This and this one remains the same. So that one, those ones are not affected. So if I apply Cauchy-Schwarz inequality on that, I have less than or equal to norm of x squared is remaining the same, plus norm of y squared remains the same. Then the one that will be changed is, you have two, inner product of x comma y, the modulus of that, okay? And then by Cauchy-Schwarz inequality, you know what this means. This is less than or equal to norm of x squared plus norm of y squared plus what? 2 norm of x, norm of y. Okay? So if you look at this plus this, it simply means that this will be exactly, do norm of x plus norm of y. If you open this bracket, square it. If you square this, open it, you have this. Recall that what did we started with? That is, we have shown that, remember that we did norm of x plus y squared less than or equal to norm of x plus norm of y all squared. So this squared, if you take the square root of both sides, what have you got? If you take the square root of both sides, it will remove the squares. Is it
norm
not?
of x
So
plus
you've got
norm of x plus y
x
less
plus
than
y
norm of x plus
is
norm of
less than
y.
or equal to norm of x plus norm of y. This triangle inequality that we are looking for, is it not? This triangle inequality for n3.
Yes, sir.
That is n3. So that's justifying n3. Okay, that's fine. That's that property. We want to look at other properties also. Lemma is also, I put it as a lemma also. Okay. The inner product, which we normally denote as this, is a continuous function on E. The inner product is a continuous function. Okay. The proof I will give you as an assignment, but it's very simple. You recall that if it's a continuous function, xn converges to x implies that txn converges to t of x. Okay, so that's what we are going to show actually. If xn, your t now is this function, inner product function. Okay, so this is actually what you want to show. In other words, if xn converges to x, you can now show that inner product of xn comma xn converges to inner product of x comma x. Okay, so that's what we want to show. Okay, so if you show that that's continuity, we discuss yet another property, and this one is very important. In fact, it is a characterization of the inner product space. Okay, so we are going to see that as a proposition. Okay, and we call it the parallelogram law. What does it say? If you have E to be an inner product space, then for x, y vectors in E, we have the following equality. We have that norm of x plus y all squared plus norm of x minus y all squared is equal to 2 norm of x squared plus norm of y squared. Okay, this is the parallelogram law, and the proof is simple. We are going to see how we can construct. To construct the proof, you just simply expand the left-hand side, and then you discover that you are on the right. Okay, how do we do that? Let me share a new screen, and then just remember this. Remember the equality, that this is equal to that. The left-hand side, which comprises norm of x plus y squared plus norm of x minus y squared, is equal to this right-hand side, which says that norm of x squared plus norm of y squared 2 times all of that. So the left-hand side is equal to right-hand side. That's the parallelogram law. To prove the, just expand the left. Once you expand this left-hand side, you see that you have exactly what you have on the right. So let me share a new screen, and then let's do the expansion and see what we have. Okay. Well, you have the norm of x plus y all squared. What's that? This is equal to inner product of x plus y, comma, inner product of x plus y. Is it not? And norm of x minus y all squared. You know, we are adding these two on the left is equal to x minus y, comma, x minus y. Is it not? So that norm of x plus y all squared plus norm of x minus y all squared will be equal to this plus this. This one will be inner product of x comma x comma x plus x comma y plus y comma x plus y comma y. Then we are through with this. The next one is plus this one, no, plus this, and this one is this, x comma x comma x. Now x comma minus y. So, but then you now have minus x comma y. I don't know if you understand what I'm saying. Then this one is minus y dot x is minus y comma x. Okay, minus y plus y comma y. Okay, so if you check this together, you see minus x comma y and plus x comma y will cancel out. These two will cancel out, right? What else? This is y comma s minus y comma s. Both of them will also cancel out. Do you see that? I hope you are with me. What do you have left? What do you have left? This is equal to inner product of s comma x, s comma s, plus what? Inner product of y comma y, plus inner product of x comma x, plus inner product of y comma y. Is it not? So this plus this is twice, which is 2 inner product of x comma s plus 2 inner product of y comma y. Which is equal to what? Which is equal to 2 into norm of x all squared, norm of x all squared plus norm of y all squared. Okay. So that's
1 minute, sir. 1 minute, sir.
okay.
It's okay, sir.
Okay, so that's one of the other characterization, which we call the parallelogram law. I want to give yet another characterization. Maybe that one I will explain. The same procedure we prove this one exactly the same way. So there's nothing special about that. That's the polarization identity. I call it proposition also. Proposition. And this is notably called the polarization identity. Let E be an inner product space. Then for arbitrarily 2 vectors x, y in E, we have the following, that inner product of x comma y is equal to 1/4 into norm of x plus y, norm of x plus y all squared minus norm of x minus y all squared plus I into norm of x plus iy plus iy, that's norm squared, okay, minus I norm of x minus iy norm squared, okay. This minus, I'm sure you know. So you have norm of x plus y squared minus norm of x minus y squared plus I, this is I, times norm of x plus iy all squared minus I, norm of x minus iy all squared. Of course, I is, as we know it in complex number, is that I squared is -1. So is the I we know in complex number. See the definition of I. I squared is -1. So you have to prove this. And of course, this one, you know, in parallelogram law, we started from the left to show the right. But this one, you start from the right. Just expand this the way we use your inner product to expand all this. Collect all like terms. You discover that you're only left with this norm of x, inner product of x comma y. So just do that. Prove. I give you as an assignment. Okay, just expand this using your inner product the way I did the last one. So that's when you expand it, you collect items. So many things will cancel out. Then you'll be left with this one, so that this and this is exactly the same. All these properties are very important. We use them to solve certain problems in Hilbert spaces. Okay. If you check your email, you will see the material. I sent 2 textbooks to you. So please kindly share with your colleagues. I've also sent to Mr. Yomi.
Okay, sir.
He will also share with, yes. So I don't know if you have seen it already in your email. You just
I've
check,
seen it.
you will
I
see
haven't
it.
opened it.
Okay. Okay, so you can share with your colleague. That will be the end of our lecture for today. The next lecture will be on Tuesday next week.
Okay, sir.
Tuesday next week, yeah, 6 to 8. So I want to thank you for participating in today's class.
Thank you, sir.
I don't know if you have any question.
No, it's okay,
I don't know if you have any question. Okay, thank you very much.
Thank you for watching. Don't forget to share, subscribe, and see you next class.